All right, during our last video, we were looking at activators for electrophilic aromatic substitution. We said that the rate-limiting step of an electrophilic aromatic substitution reaction is formation of the sigma complex, meaning this carbocation that's resonance stabilized. We know that this is the rate-limiting step because we have to break aromaticity in order to form that intermediate. An activator is a substituent that increases the rate of the reaction, so we can infer that it must stabilize the transition state where we're forming our sigma complex for this reaction. All right, so let's take a look at deactivators now. Deactivators are similar, but as you can tell, likely opposite. A deactivator will slow down the rate of the reaction relative to benzene. So I'm just going to abbreviate electrophilic aromatic substitution as EAS. And it's important to remember that we're comparing everything to benzene by itself. Benzene's just going to play the benchmark here. All right, so just like we did with activators, I want to break this down from strong to moderate to weak. So let's go ahead and look at the strong activators. And then we'll try to identify some features that make them stronger. All right, so in the first one, we've got a nitro group. So double bonded to one oxygen, single bonded to another. Can't forget charges. The nitrogen's got a positive, and this oxygen's got negative. All right, so if we look at this, there's no way for us to push any of these lone pairs into the aromatic ring without violating some sort of octet rule. So that's definitely not going to happen. However, what we could do is we could pull electron density out, right? So when we look at this entire group, one defining characteristic of this is it pulls electron density out via resonance. So a nitro group is considered a really strong deactivator. In this case, it makes this aromatic ring right here a lot less nucleophilic because we're actually pulling electron density out of the ring, which is going to slow the rate down. Due to that nitro group, therefore, the reaction is slower. So that kind of explains what's going on here. Is it's similar to what we saw with activators, but this time it's actually going to slow things down by making our aromatic ring less nucleophilic, and it won't stabilize our transition state. All right, so let's take a look at some other ones. The next one I wanted to look at is a little bit different, but what it is it's an alkylated amine. And what this is called is a quaternary ammonium salt. So amines can be alkylated to the point where they no longer have any lone pairs on them. In fact, I'm going to slide this over just so we have a little bit more room. And this entire group is considered a strong deactivator. Well, if we ask ourselves, well, is resonance possible? Can I pull this pi bond up like I did before? Not exactly. Instead, what's happening is this nitrogen with the positive charge isn't very happy, so it's just going to pull electron density via induction. So I'll just write inductive pull of electrons. All right, again, that means that this is going to be a worse nucleophile. All right, last but not least, we've got one more. And this next one is kind of similar to the quaternary amine that we just looked at. However, this time it's a carbon with 3 halogens. So if you remember, these X's right here are going to be a halogen. So that could be a chlorine, a fluorine, usually one of those two. But in this case, same idea is occurring here, right? We've got an inductive pull, inductive pull, inductive pull, but this time away from carbon, which results in a net pulling of electrons away from the ring itself. This is kind of like dipole induction or induction that we talked about earlier on this year. So it's kind of the same idea. We've got an inductive pull of electrons in either case, which means that these aromatic rings are going to be pretty crummy nucleophiles and the reaction will be quite slow. In fact, if you remember, we talked about the Friedel-Crafts reaction. We said that the Friedel-Crafts reaction won't work with any of these strong electron withdrawing groups. So let's make a note here. These groups prevent a Friedel-Crafts reaction. Because everything's so sluggish, so slow, there's just no way to get the reaction to occur. All right, so now let's go look at the moderate activators. These ones, yeah, they're still going to be slow, but not nearly as slow as the ones we saw before. And there's a variety of moderate activators. They all tend to follow a similar trend, so let me first write them down. The first one we're going to look at is an aromatic ketone. It could be a methyl ketone, ethyl ketone, doesn't matter. Next one is something that has an aldehyde. So in this case, I'm drawing benzaldehyde. Next one has an ester. And let's do a few more just to round things out. We could have something like an amine, doesn't really matter what type, or sorry, an amide, doesn't really matter what type of amide. We could have a sulfonic acid, which we showed you how to make earlier on in this video series. And we could have something with a nitrile. All right, so if we look at all of these, one defining characteristic is that we've got some sort of pi bond, one carbon away from the ring system, right? So if we think about that, we'd say, all right, one carbon, and we've got a pi bond. Over here, one carbon, and we've got a pi bond. Over here, one carbon, pi bond. This is a sulfur. We'll stick with it. Same idea. We've got the sulfur, and we've got a pi bond. Over here, we've got a carbon and a pi bond. Over here, we've got a carbon, and we've got a pi bond. That's the defining characteristic of all of these moderate activators. The one exception to this that we saw before was with the nitro group. With the nitro group, you might argue, well, isn't there a nitrogen and a pi bond right here? Yeah, but experimentally we know that this is a much stronger deactivator. All right, so all of these have this unique characteristic where we can pull electron density up and out of the ring, right? So we can do that for all of these. There's no way for us to push electron density into the ring. So they all have this unique resonance tug where they can only pull electrons one direction. If you remember with moderate activators, we had competing resonance where we could push electrons into the ring system. And some students will say, well, let's focus in on this one. That looks a lot like the moderate activators we saw before. Why can't these green lone pairs participate in resonance where they push their electron density into the ring? Well, let's try it, right? So if we do that, we could say, well, I could push it here, but then my only option is to push it up to oxygen. There's no way to get either one of those lone pairs to push into the aromatic ring. Therefore, there's no competing resonance here. The only resonance we're worried about is resonance involving the ring. So I'm going to go ahead and erase this just for clarity. All right. Last but not least, we'll look at regiochemistry, and then we'll actually skip back to our weak deactivators because the weak deactivators are kind of an odd exception. All right, so let's take a look at regiochemical outcomes. All right, so that is basically asking if we have a deactivating group, are we going to get ortho, para, or meta substitution at the end of this reaction? So let's take an example here, and I'm just going to pick a ketone. This is acetophenone. It's actually our starting material for the multi-weak synthesis. And let's consider all of the resonance structures for acetophenone, just like we did in the previous activator video. Okay, so we can pull electron density out and up to the ring system, or sorry, up to the oxygen. And that gives the oxygen a negative charge. So we can kind of see already that this acts as an electron withdrawing group. Then we can pull this pi bond over. Oops, putting my pi bonds in the wrong spot. There we go. Got my oxygen with the negative charge. And then we can keep on doing this, where I can pull this pi bond over. Oxygen still got a negative charge, but now the positive charge is over there. And then last but not least, the last resonance structure, we can push this all down. And we can show this back in its usual state. All right, so we've got all of these resonance structures that we can consider. And in this case, let's consider the hybrid view again. Okay, the hybrid view, I always show my sigma bond network, meaning my single bonds only. And then I start showing where my pi bonds are delocalized, but I show them with dashes. So in the ring system, we know that the pi bonds are completely delocalized. We know that this bond that I've highlighted is sometimes double, sometimes single, so it's kind of in between. So let's go ahead and draw that as a dash bond too. So I'll go ahead, and draw that as a dash bond. And then the carbon-oxygen bond sometimes is double, sometimes is single, so we know that that's in between. So I'll go ahead and draw that as a dash bond. And it looks like that's it. All right, next thing's next. Sometimes this oxygen is negative, sometimes it's neutral. So I'll go ahead and indicate that using a partial negative charge. All right, if we look at the carbons on the rings, sometimes they're positive, specifically in these positions that I've highlighted. So I'll go ahead and write partial positive, partial positive, partial positive. All right, so now we can consider this hybrid structure reacting with some sort of electrophile. All right, the question is, will one of these ortho or para positions react? Probably not, right? We don't want a partial positive reacting with an electrophile that has a positive charge, right? Those two like charges will actually repel one another. So that's not going to happen. So instead of those ortho or para positions, the one that makes the most sense is the meta position, the one without that partial positive. So in this case, either one of these metacarbons relative to that electron withdrawing group would be highly reactive. Due to the symmetric nature, it doesn't really matter which one you pick. And I'll show you why. If we have it react with this meta position or the other meta position, we're actually going to get the exact same compound, right? Because if you number it, right, this would go 1, 2, 3, where this one would go 1, 2, 3. There's still 1, 3 substituted relative to one another, so it doesn't really matter which one you show. All right, so now let's take a brief look at the exception to all of this, and that's halogens. Halogens are odd. So let's go ahead and just briefly make a list of why halogens are odd. Whoops, and I'll go ahead and just indicate that the halogen could be any halogen. Doesn't really matter which type, so I'll just write X equals halogen. And the first thing that we know from our experimental observation is that the reaction is slower than with benzene. Specifically, let me even rewrite this. The EAS reaction. The electrophilic aromatic substitution reaction is slower than with benzene. All right, so that's a good experimental observation. Question is, does that mean that it's an activator or a deactivator? In this case, if it's going slower, right, that means that it must be a deactivator. All right, so that's one experimental observation that we've seen. The question is, well, why would it be a deactivator? Well, we know that a deactivator pulls electron density out of the ring, making the ring less nucleophilic, right? So I would propose that this is likely due to the electronegative nature of halogen atoms, right? So we could say that it's a deactivator, and the best reasoning we can come up with is due to the inductive pull of electrons. Oop, that doesn't really make sense. I forgot my 2 in there. So let me slide this over, and then we'll add the 2 in. So due to induction. All right, so that's a really important experimental observation. The next thing we could do is actually run a reaction. All right, so let's say I've got a halogen right here, and I react this with an electrophile, and all I do is I look for the products. We can't see a mechanism in solution, but we can see products, right? All right, so this is one product. We could determine that by NMR. And then the other product that we observe looks like this. So this would be the experimental observation that we would get out if we were to run this test reaction. And what you would immediately notice is you'd get para substitution and you'd get ortho. Okay, so this is a unique thing, right? If we look at this, in fact, I'm going to slide this whole thing down. This tells us that this is an ortho-para director. Okay, so this is the weird thing, right? Let's go back. Over here, I just finished telling you that deactivators are meta-directors, right? And both of these structures are electrophile, even though it's the same product, installed itself in the meta position, right? Where halogens, we just said they're deactivators, but they're actually ortho-para directors. So then the question is, well, why would they be ortho-para directors? Well, let's come up with an alternate theory. One theory that seems to make the most sense to me, at least, is that we have these electrons on the halogen that do have resonance and can dump electrons onto this ortho position. Or if we continue pushing those arrows, we can actually push everything down to the para position. So the best way to rationalize all of this is to say, well, resonance must be the reason why we're getting ortho-para substitution with our final product, but we know experimentally that the rate's slower, so it must be a deactivator. So this is kind of the weird exception to everything. All right, so that's where we're going to stop today. For our next lecture day, what we're going to do is we're going to start looking at synthesis problems, especially if we have multiple substituents. So what happens if we have both an activator and a deactivator off of an aromatic ring? All right, talk to you soon.